before we start our debate, I would like to show you a slide which explains some terms, technical terms, and I think it's really important that everybody understands what we are talking about to see the difference between shale oil, shale, and shale gas. So just you can read it rapidly. Okay, and I think what is interesting, what we can see from this slide, that in the general public, the most known representations of unconventional is shale gas and tight oil. So, Mike Dawson, I will start with you in order to talk about the situation of unconventional in North America. So, what are the new exploration themes in unconventional?
Thank you very much. I think, first of all, we need to distinguish between the North American technology situation and in the world as well, because North America has had the advantage of at least 10, perhaps even 15 years of unconventional resource development. They have a long history of developing the technology, the core technologies that were primarily horizontal drilling coupled with multi-stage fracturing and a newer technology, multi-seismic or microseismic monitoring. Compare that to in the rest of the globe where the unconventional resources are emerging resources and the companies or the governments are still trying to determine what are the technologies that are going to unlock these basins. While shale is shale, the resources are going to be different, the basins are going to be different, and it isn't always applicable to take analogies from North America and try to apply them to other regions around the world where the geology and tectonics, the geomechanics are all going to be different. So I think it's important to differentiate that, but if we talk about North America, the biggest challenge we have and where the technology is evolving is driven primarily by commodity price. Because of the low prices of natural gas, companies are shifting their emphasis away from dry natural gas production towards liquids-rich natural gas production or tight oil. That presents some more unique challenges in terms of how the molecules flow. Oil molecules are going to flow and have a different size. They're going to flow differently than what is a natural gas molecule. So the way you drill your wells, the way you fracture stimulate your wells are going to be different. And so as companies make that shift in order to survive economically, they're going to be faced with newer challenges relating to dealing with a different type of hydrocarbon molecule.
So in a previous conference held by the Total University, we discovered that tight oil production would rise to 4 million barrels per day in 2020 in the US. It means that US will become energy independent. What are, for you, from your point of view, what are the technology challenges for this tight oil and liquid gases?
Again, going back to, so from a pure technical perspective, it's how do you produce a predominantly liquid from the reservoir as compared to a gas. But the biggest challenge that we have is trying to balance the technology that is unlocking these resources with commodity price and oversupply. We saw dramatic changes in 2008, 2009 and onwards where the application of technology to these emerging basins within North America led to a dramatic oversupply of resources and a dramatic drop in natural gas price, which in fact to some extent today is even not economical for many of the resource plays. There is a risk that as we develop as companies have shifted much of their capital and their emphasis towards the tight oil and the liquid-rich play, we're already starting to see the effect of technology unlocking these resources and then having an oversupply start to build in North America of those commodities as well, which will have potential implications in terms of pricing.
So it means in the US there's no need for technological revolutions, so the unconventional resources are extracted in the same way than conventional?
I know that the technologies that are driving the unconventional resources, and I'll lump oil and gas together, is really predicated on the two fundamentals being horizontal drilling and multi-stage fracturing. And so as we advance the technologies towards improving on those two core foundation technologies, what we're seeing is companies are becoming much more proficient in drilling longer laterals, more exact placement of that horizontal lateral within the formation at a lower cost, and at the same time becoming more effective in terms of how they are placing their fracture stimulations. We found that we're finding now that perhaps particularly in oil, tight oil, that applying the fracture technology that we've used for shale gas is not necessarily the best technology. And so different types of fracture fluids, different types of proppant materials may be better in terms of doing less damage to the reservoir.
But regarding the productivity of a horizontal well, do you think there's always room for improvement? What kind of technology?
Oh, absolutely. I mean, there's two aspects of improvement and efficiencies. One is an individual well itself in terms of becoming more productive at a lower cost. That's driving the innovation in terms of, as I mentioned, the types of fracturing that is being done, the types of fracturing fluids that are being utilized, the volumes of fluids and proppant that are being used in order to control costs while at the same time achieve efficiencies. But then there's a bigger picture in terms of this is a technology play where statistical production is a critical component. And so being able to develop these projects in a larger economies of scale where you have the advantages of more effective materials management and gathering or collectiveness of all of your services is going to lead to improvements. So while one individual well you need to drill better, and companies are striving towards that, it's the coupling of a program where you're drilling multiple wells from a single pad that is having the largest impact in terms of efficiencies and improved productivity.
Okay, thank you. Scott Stevens. So let's talk a bit more about the technological innovations. What are the big new innovations, big new technologies in US shale?
Well, it's very much like Mike just introduced there, and thank you very much for inviting me here, by the way. And just before I get into this first slide, I'd just like to point out that what's happening in the U.S. and also in Canada, it's not just a technology story, it's really a business. And we have kind of unique conditions, especially in the United States, where we have private ownership of mineral rights. That means the farmers own the minerals, not the government. And we have really a very hands-off policy by the government. There's no tax credit for promoting shale development. There hasn't been one for over 20 years. And so what you have are dozens of companies, mostly independents actually, and then increasingly the majors buying into these plays that have driven this technological and business revolution. So I think it's interesting to contrast that with the conditions, say, in China or in Europe, for that matter, where the government is probably going to have a much stronger role. So just to look at this first slide here, I'll just draw your attention to the upper right diagram there. You recognize this building, I hope. And this is a cross-sectional view of a real-time seismic monitoring where you're actually listening to the noise and mapping out the noises made during the frac job as the rock is cracked with high-pressure sand water injection. And so each color is an individual frac stage. And what this is telling us is that, at least for this well, which is in the Eagle Ford Shale in Texas, it was a very uniform and a very effective frac. And so this is a way to actually measure the effectiveness of the frac and maybe make adjustments on future wells so that you don't have gaps in the lateral, in the intensity of fracking. And it's also a way to actually guarantee that we're not growing this frac up into the shallow aquifers. And then that's what this lower diagram is showing. That's a cross-sectional transect across the entire Barnett Shale play, which is about 100 miles across or so. And you can see these shallow blue wells, which are the water wells that are, of course, 100 meters or less generally. And underneath that are hundreds of individual wells showing the height and the depth of the frac, of the hydraulic fracture. And in all cases, there is at least 1 or 2 kilometers of unfractured, unstimulated rock, which is really buffering, protecting the shallow aquifer. So this is really a two-edged technology. It helps to improve the recovery factor which currently is only maybe 25% of the gas in place and perhaps 7 to 10% of the oil in place. And it's also a way to demonstrate that we're not polluting the shallow aquifers, I think.
And do you have the time to experiment this new technology?
Well, it's, again, because of this unique business situation, and especially in America, where there was in the 2000 to 2008 period, there was a realization that we suddenly could develop shales. So they're followed by a land grab. And because it's a private contract, you have a very short time fuse to drill the minimum commitment. It's called HBP, held by production. So there was actually a kind of a frenzy of drilling by 50 or 60 companies all across the U.S. And it was really more for the purpose of holding the acreage in the long run. And so now that much of this acreage in certain plays is HBP'd, I think the operators have the luxury of taking more time and doing a more rational development plan with real-time seismic monitoring and maybe with pad drilling, for example, multiple wells, 8 wells, 12, 16 wells from a single location, which is, of course, a much smaller footprint and even reduces the cost by about 10-15% per well.
So are there any other new technologies that you can present us?
Yeah, I think the next slide might show. Yeah, this is another idea here. Here's a real-time mineral logging where you're looking at the, shales are complex rocks and they consist of various minerals. And some minerals are very good. They're very frackable, such as quartz, feldspar, calcite. These are very brittle, glassy minerals. But other minerals, and the glassy ones are shown in red here, the other minerals are more ductile, and that would be the clays, the illites, and so on, and they're not so frackable. So in this new technology, which is really not new, it's just a new application of an existing technology, you can help to steer the lateral into the most brittle part of the shale, and then once you finish the well lateral, now you can custom design the frac to suit the specific brittleness of that lateral, whereas today we really the industry just applies a cookie cutter approach so that you divide this 4,000-foot lateral into 20 stages and every stage gets the same recipe. I think in 20 years we're going to be going to look back and laugh at how simple the world was with these new technologies.
And is everybody doing this? Using this?
No, this is not being used hardly at all. It's really very new. And it's got a lot of room, and I think by doing this more widely, you can increase recovery factors perhaps from 25 to maybe 40 or even 50% of the gas in place, and maybe a suitable uptake in the oil recovery factor. So not only are we discovering new plays all the time, in fact, last week Continental Resources said they had a 1.8 billion barrel net new discovery in southeast Oklahoma. It's the Woodford Shale. Unrecognized play, but you also have this better application of extraction technologies.
Okay.
So there's really no limit. I mean, not in our grandchildren's lifetime, certainly.
Okay, is there any other technology to improve the wells?
Well,
No.
maybe I'll let other people, they surely have ideas as well.
The tracer, I've heard about the
Oh,
radioactive tracer.
Well, yes, of course, you can inject...
Perhaps we can ask, is there any other technology?
We could go on all day.
suggestions?
Yeah, there's geochemical tracers that you can use
Chemical,
by
yes.
mixing them with the frac fluid and then later, logging that. Although by that time, it's a little bit too late for that specific well. But for the future wells, then you can help optimize the frac. Yeah, the frac is really what produces, without the frac, there is no production from these shales. So all of the R&D, I think, really has to focus on the frac itself.
Okay, thank you. So Mike, can you tell us what are the leading companies using these new technologies just described?
As Scott mentioned, much of the innovation is being driven by the large independents within North America. Really, it's companies that have a very large land position and have a strong capital base available to them that have the ability to spend some dollars in the research and development part and recognize that while unconventional resource development is very much a technology play, it also is a play of economies of scale. And so in this slide here, you can see an example from Encana, where over the years, they have been able to drive their costs down, their supply costs down dramatically, so that even in a time when there is dramatic drops in unconventional or in natural gas pricing, they've been able to be competitive because they've been able to take their learnings and continue to tweak the model so that they continue to improve. Much of the improvement is being driven by changes in terms of their fracture stimulations, but also being driven by supplies and material management efficiencies.
So, okay, I think we understand that now the wells are getting more individual. Is there any technology that makes the wells more efficient and that reduces the footprint of these more individual
Absolutely.
wells?
We've talked a bit already, both Scott and myself,
yes, perhaps you can
about drilling multiple wells from a single pad. And you can see in this slide here the effectiveness of reducing the surface footprint by drilling all of these wells and then having them geosteered in specific geographic directions. That allows, number one, to reduce the surface footprint. It also allows being able to amalgamate a lot of your activities into one location from an efficiency perspective. But also, when you look at the pattern that has been being laid out in these wells, you're also becoming more effective and efficient in terms of draining the reservoir in the most effective manner. The other aspect that goes hand in hand with this horizontal drilling is the multi-stage fracture stimulation that Scott referred to, and being able to realize and be able to monitor what fractures are doing in real time using microseismic imaging. That allows you not only to control in real time where the frac is going vertically and to some extent horizontally, but also being able to visualize how effective you are at stimulating the entire reservoir over the block of area.
And are there any other technologies that can reduce the footprint? Because reducing the footprint is a key issue.
Absolutely. And one of the key elements, and it came foremost with the number one concern in the surveys that was done that we saw earlier this morning, was about water usage and water conservation. And so companies are recognizing that it's not sustainable to be using large volumes of water, which is the fracture fluid of choice at the present time. It's not sustainable in the long term to use freshwater surface supplies of water. And so a company like Encana, who's operating in the Horn River Basin up in northeastern BC, have developed an integrated water treatment facility where they're using formation water, bringing it to the surface, and treating it, using it for fracture stimulation. The flowback water that comes back after the fracture stimulation is then captured and pumped into that existing formation at a different location for subsurface storage. And so you have a closed loop, and you've eliminated almost 98% of all surface usage water requirements. Another aspect is using multiple activities on one well site at the same time. On the previous slide, you saw a drilling activity and a fracture stimulation activity all occurring on the same pad. So multitasking of services allows greater efficiencies in terms of operations.
So, Scott, let's talk about Europe. With you, are there any innovations that can resolve Europe's shale drilling problems?
Well, I do have a slide here. I just would like to point out, I mean, Europe has tremendous shale gas and shale oil potential, but not necessarily the best structural geologic setting. And I'm not to pick on Europe, but China, India, many countries are tectonically complex. And I like to show this because this is a contrast between a very simple, typical North America shale basin. This is the Niobrara in Colorado. There's a 2D seismic showing very simple geology. We're not really looking for natural fractures. We're actually going to just engineer the fractures, so we don't want a lot of faulting. And horizontal drilling, of course, is going to intersect these faults. That's a cross-section down there I made actually for coal bed methane in Poland some time ago. And you'll see that there are a number of faults. Most of the European countries are heavily faulted, and it really limits the length of the horizontal lateral, I think, because these are significant faults, and so once you cross the fault, you're no longer in the shale. And there may be questions about whether the faults are wet and so on. And every well becomes like a little science project, so it's quite costly. So I don't want to say it's not possible for Europe, but it's going to be very challenging, and I think looking back at the coal bed methane record, there is no commercial production of coal bed methane anywhere in Europe, although we tried very hard in the last 10, 15 years. So I think it's going to be a big challenge, and certainly many, many vertical wells is probably not going to be the answer.
So is there any competing technology to fracking?
Well, this is more of a drilling challenge. How do you get horizontals into this kind of complex geology? Perhaps the laterals are just relatively short. Maybe you can't go 2-3 kilometers like we often do in North America, but there may be areas. The good thing that Europe has, of course, is a very high gas price. So you have 3 times the gas price we have, so you have a lot more to work with. So maybe there's an optimum in there. But certainly taking Canada is actually the most advanced because the Horn River is such a remote area, and it's very hard to construct these well pads. They're going out really, really long distances. But I don't think that's going to be the answer for Europe. Okay. I don't know the answer, actually.
I think nobody knows the answer. So thank you. Now let's talk about new technologies and concepts in conventional oil with Ashok Belani, Judson Jacobs, and Jean-Jacques Jarrige. And I will start with you, Ashok. You are from Schlumberger. In which domain conventional and unconventional innovation is creating new potentials?
Well, first of all, good morning. Thank you for inviting me. I thank Total for actually giving me the opportunity to be here. I work for Schlumberger, which is a service company, and we do practically all of the technologies that have been mentioned so far. So it's kind of nice that I don't have to talk too much about them because they are mentioned by my colleagues already. I think there is innovation going on in all of the different phases of the drilling in unconventional and in conventional as well. So in unconventional, without repeating too much, there are 3 aspects that make the unconventional possible. There is the aspect of characterizing the rock. You have to characterize the rock for its producibility. To characterize the rock for its producibility, you have to measure the minerals or the parts that are producing, and then by correlating it to a spatial measurement like a seismic, you figure out where to place your wells and how to place your wells. And then after that, in drilling, we do things like pad technologies or say pad drilling, where today in Ghana, that was mentioned a few times, is actually planning a pad with 50 wells from the same pad location. And that pad location will have all the energy and water resources for all of the 50 wells, and to be able to put more than 30 stages per well to be able to maximize the production per well. And that's a very efficient way of approaching the problem. Basically, all of the activity in characterization or in drilling or in stimulation is focused on trying to optimize the resources or minimize the resources. And the resources are in terms of energy that is used, energy used in the pumping or in the trucking that is related to it, or the resources used in terms of water and sand and the chemicals that are pumped into the formation, to be able to do all of these wells more cost effectively and with a lower environmental footprint. And the lower environmental footprint obviously brings with it the social and the economic commerciality of the project. So in all of these aspects, there are many innovations that are going on. All of the people who have worked in the industry for the last 30 years could not have imagined even 3 years before now that the United States will be producing 1 million barrels of oil per day from these tight reservoirs. So the amount of innovation obviously is quite rapid and is quite significant. And in the conventional domain, and we call it conventional because the reservoirs are known from the past understanding of geology, there is also innovation. This innovation continues to bring new methods of exploration, of development, so drilling, and also for completion or the engineering of the well for the life to be able to produce for a long period of time. So in the area of exploration, there is a lot of advancement in geochemical models, and these geochemical models basically explain how the basins have the petroleum that is produced from there. And this has led to, for instance, discoveries even in Norway or in new places like the carbonates in Brazil and so on. There is obviously improvement in geophysical techniques, and I'll talk about that a little bit later. In the area of drilling, we are drilling in deeper and deeper water, and we are drilling in deeper and deeper formations, and hence the geomechanical aspects of being able to place the wells in these difficult areas requires a lot of innovation to happen. And at the same time, in completion, well completion techniques, this is still evolving. Many of the discoveries that have been made in the Gulf of Mexico or in the North Sea, even in Brazil, today are actually not exploitable with the current completion technologies that are available. And these completion technologies are being developed with collaborations between the oil companies and the service companies. At the same time, I think an important area of innovation is what are subsea production systems, because we put production systems on the seafloor nowadays. And on the seafloor, there's a lot of advancement. I think there's going to be some conversation on that later on in the afternoon, but I'll talk about it as well a little bit later. At the same time, for these offshore developments, we have to look at well integrity, and well integrity is an important safety aspect of drilling of all these reservoirs and their production, and there is a lot of innovation in this area as well. So by and large, both for unconventional and for conventional, there is a lot of innovation that goes on.
But now we're going to talk about conventional. So, avec Jean-Jacques Jarrige, what are the new frontier themes or innovations in conventional oil exploration?
Yes, good morning, everybody. What we mean, I can start by defining what we mean by frontier exploration. For us, is going beyond the technological or geological concepts. So in the following, I would like to emphasize, to point out the role of innovative concept in exploration. There are three ways of doing it. This is not the slide, but anyway, I can go ahead. There are three ways of doing it. The first one is to transfer an old idea in a new basin. That is a classical job for geologists in an oil company. The second way is to have a new idea in a proven oil and gas province. That means a breakthrough in this province. And the third way, which is paradise, which I will say is a nirvana for geologists, is to have a new idea in a new basin. So on this slide, I have summarized the most significant oil and gas discoveries in the last decade. I list the places in which these discoveries have been made. So you can read it by yourselves. And I can go through the three types I've described. So the first one, having an old idea in a new basin. For instance, Graben and Rift. There are very old petroleum basins, proved petroleum oil and gas basin. The best known one is the North Sea, for example, of course. And the trick is to transfer this know-how in a new area, in a new basin. I can select as an example the Uganda case. In 2007, there was a discovery around the Lake Albert in Uganda. Uganda was a very underexplored country before this discovery for two reasons. The first one, this area is located about 1,000 kilometers from the seaside. So you see the economical threshold for a project was very high. And the second problem was geologists did not think in this so recent basin they can find significant volumes of oil to make to the project flying. So after the discoveries, the boldness of the explorationists, of geologists, geophysicists, and reservoir engineers was to convince themselves that it was possible, and themselves first, and their management after, which is not easy, to convince them they may have a project there, and to have a project, they have to demonstrate to says there is a fair probability to find there over 1 billion barrels of oil. So you see the problem. This is boldness in exploration.
Okay, and Ashok, what do we need to make this model productive, this type?
So I think, as Jean-Jacques mentioned, we are talking about old ideas in new basins. So the innovation here is not in the idea. The innovation is how do you move those ideas into the new basin. So most of the time, these are new provinces, and the risk is bigger in these new provinces. The costs are higher. The infrastructure is unavailable, and hence the whole effort is on trying to bring down the cost as far as possible to make all of this viable. So again, I go back to the fact that there are much more. If you take the areas which were mentioned by Jean-Jacques, you may have East Africa, offshore or inland, or East Mediterranean, or the South Atlantic on both sides of the South Atlantic. All of these areas are new, where ideas are being applied from elsewhere and new discoveries are being made. In these cases, we try to improve as much as possible the geological or the basin models for the geochemistry to be able to place the wells correctly. And the geomechanics are a little bit different from the other places, and hence drilling has to be, we have to optimize the drilling to be able to make the wells more cost effective. And as we make them more cost effective, we make these areas more and more viable in the future. For instance, a very interesting area which is just coming on surface. In fact, there was an announcement just last week about Saudi Aramco making a discovery in the Red Sea. It's for the first time ever in the Red Sea that there is a discovery, and it is going to open a completely new frontier for many years. But these are ideas that will be transported from the rest of the world to a place like the Red Sea. But the Red Sea has its own geomechanical issues, and these geomechanical issues will be solved by these newer techniques which will make the cost come down over a period of time. At the same time, I think there needs to be a lot of innovation in the logistics and the supply chain aspects in these new areas, because they do not have the infrastructure like many of the other provinces have, and there is innovation to be made there. I think there is also this issue of people competency, and along with the infrastructure, the people competency needs to be developed as well. And for that as well, you can use technology and innovation to make these places more cost effective. So another area that I should mention is that most of these new places are somewhat remote. And because they are remote, and in many cases they are offshore, so there are subsea developments. And in the subsea developments, a lot of innovation needs to happen to really optimize how much we do on the seafloor versus how much we do in the well and how much we do on surface. So there's a lot of innovation that need to happen.
Okay, so Jean-Jacques, let's continue with your presentation of the new concepts, the second one.
The second type is to be innovative in concept, is to bring a new idea in a well-known basin. The most known recent example is the case of the pre-salt discoveries in Brazil, in the Santos Basin. So we knew for a long time, the interest of pre-salt plays, for example, by discoveries made in Africa, in Gabon or in Angola or Congo, in clastic reservoir. In Santos, the production used to come from a post-salt reservoir, but in 2007, they drilled below the salt in the deeper part of the margin, about 2,000 meters of water, and they found carbonates, oil-bearing carbonates below the salt. So we knew this kind of situation, carbonate just below the salt in other countries, and generally the reservoir quality of such a reservoir was not very good. But in the case of Santos Basin, the quality of reservoir was very good. And that is a big change in this play. Another problem is generally below the salt, the quality of the seismic is very bad, and it's very difficult to image below the salt. On this slide, you have two examples on the right side of the slide. The salt is in pink, And on the upper part, on the seismic profile in the upper part of the slide, you can see a processing made in 2007. And so the possible prospect is just below the salt in the hidden area where there is no good definition of the horizons. In 2010, there was a new processing with new technology and bigger computers. And you see at this stage, it was possible to define the geometry below the salt. So at this stage, there is a possible prospect, drillable prospect below the salt. So you see the drastic change in the seismic imagery through this example. That means for oil companies, a tremendous effort in increasing the volume of calculation and the potential of computer. On the diagram, you have a sketch showing the increasing of volume computation in oil and gas. Around 2000, we were at the stage of a teraflop operation by second. And oil companies like Total, for example, increase in a very short term period of time, 10 years, they drastically increase the potential of calculation from 1 teraflop to 1 petaflop operation by second. That means an increase by 1,000, which is tremendous.
And so, yeah, Ashok, always the same question, what technologies were needed to make this viable?
So I agree with Jean-Jacques completely that for the exploration, there has been a tremendous development in the area of geophysics and seismic. When you look at the Gulf of Mexico or the North Sea, West Africa, Brazil, these are all fantastic examples where significant new reserves have been found using all of these innovations. So I'll give you some statistic to bring out the point. I think the area of seismic acquisition and geophysics processing is probably, when I look at the total portfolio that we at Schlumberger maintain, this is probably the area of the fastest development in technology in the oil and gas world. In the Gulf of Mexico alone, in 2007, I think it was, where we realized that the fact that you made seismic acquisition in one line, or sometimes you got better data or different data from a cross-line measurement, we decided that we need to look at the rock from all azimuth from different directions. So there was wide azimuth experiments that were done in 2007 and 2008, where we used 7 boats at one time. And eventually we settled down on using 4 boats, 2 source and 2 receiver. And that acquisition went on for about 2 years. Then we used the coil technique, where we actually took the boat around in a circle. And then today we use 4 boats in a circle, and we are able to get offsets, which are 14 kilometers. And so we are doing this 2x4 dual coil with kilometers of sensors in the water, which are in oblique directions. These are extremely new kinds of acquisitions, which are changing almost on an annual basis. So the pace of change is quite significant. Now, all of this also acquires a lot of data, and the algorithms to process these go from things which were very simple in the past to the migration techniques, which are significantly more complex, and inversion techniques, which are significantly complex as well. So in this respect, to support the chart that is on the board right now, in Houston, for instance, we used to have, in the year 2007, a compute power of something like less than 100 teraflops, maybe 50 teraflops. And today we have something like 15 petaflops in a single building churning all of this data. And interestingly, most of the petaflops in that building where we have 15 petaflops are coming from actually NVIDIA graphics processing technology. So it's a good thing that all our children played all those video games, because all of that technology that came with it actually makes this seismic processing happen in a much more significant, in a very efficient way. So there are these technologies developing all the time, and I think we today actually have roadmaps that go up to exaflops as it is shown on the chart, and all of this will keep developing for the next 5 or 6 years to come. At the same time, in drilling, there are many advancements, and in drilling, most of the advancement comes from the fact that there are many different functions that are performed on a well, which is going significantly deeper to depths like 35, 37,000 feet, going in 10,000, 11,000 feet of water. Here we have wells which go 7 different casings telescoping down to the bottom. Each of the casing tries to shut off one pore pressure regime. So separating these pore pressure regimes, drilling through the salt and sediments below is quite complex. And so many different aspects of the rig functionality, people on the rig have to work at the same time, simultaneously with people who are the designers and planners who are in the cities where the oil company functions from. And all of these people are monitoring all of this in real time and adapting the well to be able to drill it and place it in the right spot. So real-time measurements on the drill string and in the formation, they help to make these wells safe and also to put them in the right place.
Okay.
At the same time,
Yeah.
so I'm also going to mention that in the subsea area, there is a lot of development to come as we put almost subsea factories on the seafloor, which will have their own power and their own process capabilities, which is quite complex. This is quite like rocket science. It's actually more significantly complicated than putting a rocket into space, because you are doing all of this in 10,000 feet of water. It's a significant challenge, but the industry is targeting it. And at the same time, then the innovation needs to happen to keep the well integrity or the production system integrity in place, such that this can work reliably for a long period of time. So the pace of innovation here is quite rapid, and a lot of technologies are being put into play. Every field that is developed has something new happening all the time.
Thank you. Jean-Jacques, what is the third
Yeah, the
type
third
of new
case,
concepts?
which is for me the genius case, is to find a new play in a new area. I have in mind the Jubilee discovery made by Tullow in Ghana 4 or 5 years ago. And usually the prospects we are looking for are closed structure, and the hydrocarbon have been trapped in this structure. But in this case, Tullow found what we call an elephant. That means that over 500 million barrels without any obvious structure on the seismic lines. Just a sketch here on the screen to explain what the difference between the classical plays in a passive margin and the new play. On the top, you have a classical cross-section through a passive margin, like South Atlantic, and the dark areas shows oil and gas accumulation, which are either in a closed structure, anticline, or rollover, or behind fault. And all these kind of geometries have been induced by a general gliding of the sediments of the margin above a salt layer or a clay layer. This is a classical way we are looking for in passive margin. In the case of Ghana, it's completely different. You don't see any obvious structure. You don't see any fault, big fault in this case. And the trap is formed just by the wedging, regional wedging of the reservoir towards the continent. So on the seismic, especially on 2D seismic, it's not obvious to locate this kind of trap. Of course, after such a discovery in a place or in a basin, after the discovery, it's too late to be competitive for a company to be competitive in this area. If you try to come in or to farm in, it's very expensive, so there is no economy in the new project. So what you can do is to understand very quickly the key of success of such a discoveries in this area, and you can transfer by analogy this new play in another area. That was done by Total, Shell, and Tullow. Geologists had in mind that 100 million years ago, the South Atlantic was closed. So in front of Ghana, on this margin, there was the South American margin. And surprisingly, there was a French part of our country there, the French Guiana. So we took a block in this area on the same ID, and we made the discovery of Zadius, which could be also a big elephant in this area. So it's a new play, and the idea is coming from Ghana. So Total, on the same tram, in the last months, has taken blocks on the same reasoning in Uruguay, in Bulgaria, in Kenya offshore. So even if you don't have the idea by yourself, if you react very quickly, you can transfer this new concept in other areas.
Okay, so thank you very much. Judson, at least Judson. So you're a director of his CERA's Upstream Research Group, and we have seen there are a lot of challenges and a lot of opportunities. But what does this impact? How does it impact the global oil and gas discoveries?
Great. Well, thank you very much as well. So to answer the question, it might help to provide a bit of context. Over the last 10 years, we've seen that we've totaled about 240 billion barrels of oil equivalent in discoveries. And this is actually a bit of an uptick over previous decades as well, and really actually begins to reverse the the downward slope that we've begun to see all the way since the 1960s. The majority of these discoveries still take place in well-established plays that have been around for a long period of time. It's really been, we're 25 what we refer to as play openers over the last decade. And these are the types of things that Jean-Jacques referred to pretty extensively during his discussion. These are the types of things like the pre-salt in Brazil, in which greater seismic imaging combined with drilling technology allowed us to discover some of the pre-salt resources. The French Guiana, by looking across the Atlantic and seeing some of the analogs that were there. Looking at East Africa and using some of the improved seismic imaging together with non-seismic remote sensing technologies as well. So all of these 25 play openers have contributed about 20 billion barrels equivalent of the overall 240. And this shouldn't be discounted by, there's about 10%, is that not only have we been this higher than we've seen in previous decades, but it's also led to significant discoveries in addition to those initial play openers as well. So they're pretty substantial. One of the other trends that we see is the movement to more technically challenging operating environments. And just over the last decade as well, is that almost nearly a quarter of these 240 billion barrels of discovered resources have taken place in the deep water. And especially the ultra-deep water has actually been the ones that actually stand out to be the most significant here. And it's really, if you begin to think about where some of these discoveries are taking place, actually, next slide. Oh, is that right? Okay. Missing. As you begin to look at where some of these discoveries are taking place and really kind of reaching out where some of the play openers are, it's beginning to have a bit of a rebalancing of the global oil and gas industry. And we're shifting a little bit away from the industry stalwarts, such as Russia, Norway, and possibly even Saudi Arabia, towards some of the new and upcomers, such as Mozambique, Turkmenistan, and even the United States of America. So really it's having a significant impact on the industry, and I think this will continue over the next decades as well. So one other interesting observation we've made, and one of the trends we see, is that over this period of time, in which we've had these significant discoveries over the last 10 years, at the same time, what we've seen is that we've begun to stagnate in what we refer to as exploration and drilling success. We had a long, steady climb up from about the 1960s, when we were about 20% success rate, up to about 40% in the early 2000s. And that stayed about the same. Despite these advances that Ashok was speaking about and all the other ones as well, we haven't had the game changers, but at the same time we've had slow incremental improvements. And we look at it not that we're kind of running with our, kind of spinning our wheels, but it's much more that we're pursuing many of these much more technically challenging plays, and we're really beginning to see that, trying to achieve success in them is much more challenging.
And so what can we expect in the future, in the forthcoming years, up to 2030? Do you think that these exploration successes can really will influence the oil discoveries, the oil production?
Yeah,
gas production?
so absolutely, and many of those of you who are involved in the oil and gas sector recognize that there's a pause, there's a bit of a respite between when the discovery is made and when you actually begin to see production flowing. And so what we see is that many of these interesting play types that are just beginning to open up, they represent very modest production volumes at present. So if you, for example, if you look at the ultra-deep water, which is gaining so much press these days, there's actually less than 500,000 barrels a day out of the total 92 million barrels a day of oil that's actually flowing out there. If we look forward, we have projections, we see that actually rising to about over 4 million barrels a day by 2030. What you see is that currently, really ultra-deep water production, which we define as deeper than 1,500 meters, there's really only 2 countries that are actually producing from these types of zones, the United States and Angola. By 2030, when we increase that to up to 4 million barrels a day, there are going to be more than 10 countries that are going to be producing from ultra-deep water reservoirs. Another great example, I'll go back a little bit to the unconventional, which we've begun to reterm. We actually call it uncooperative, because there's such a gray line between what is unconventional and conventional. But uncooperative reservoirs, especially around kind of some of the tight oil, it's been a massive growth. And we see that whereas production is currently about 2 million barrels a day, largely in North America, largely US, but some in Canada, we expect that to grow to between 5 and 6 million barrels a day by 2030. And it's really quite remarkable. If you look at the growth that's happened, especially in the United States, is that we've gone from very low amounts to 2 million barrels a day. In the last year alone, we've increased our production by 1 million barrels a day. We doubled in the last year, something that took decades to be able to achieve. And as you might imagine, the pace of development and the frenetic pace of development has actually been pretty astounding. So if you look collectively, and this is a graph that actually looks at the end of easy oil. That's something that's a commonplace saying these days. But if we look at the resource types that actually make this up, such as the ultra-deep water, the technically challenging ones, we look at the tight oil, some of these other ones we began to talk about, and finally, if we throw in heavy oil there as well, some of these more really technically challenging ones, we see that at present it's relatively modest. It's 10%. We expect that to grow to double as a percentage of total global productive capacity by 2030, even as overall capacity grows by 20 million barrels a day. So pretty substantial. Gas, and I'll finish up with gas. I know we've had a lot of discussion around there and the successes that we've had in North America, representing currently over 50% of production is from shale gas and tight gas. We expect that to grow to greater than 80% by 2030, even as production nearly increases by about 50%. The real challenge, I know some of the technical issues associated with kind of exporting the shale gas, as we refer to it in North America, some of the technical challenges are real. But especially in developing some of these, in tight oil as well, we see that the above ground issues are much more significant. Whether it's the ownership stake, whether it's having the infrastructure in place, whether it's the presence of the service sector to be able to enable it, is that we look around the world, and we've done this. And we look around the world and we see significant resources. We have some concerns, and we're not always as optimistic as we might be around the pace of development that might occur there.
Okay, so thank you. Let's talk rapidly about the perspectives with you. Scott, what will be the next type of resources or the new shale gas in 20 years?
Well, I'm not a visionary. I'm really kind of a shale CBM person, but everybody knows that offshore, especially on the continental shelf, there's vast deposits of hydrates, which are icy deposits of water and methane gas. And we've known that they're there. You can see them on seismic. The volumes are literally thousands of times the conventional oil and gas resources. The principal challenge has been on the recovery side, the engineering, because as soon as you contact this, drill a well or inject or try to produce, it melts this very fragile hydrate, and then the well becomes unstable. So how do you actually maintain a stable well over time is really the challenge, and that really is the sum of my knowledge on the subject. So maybe others.
And apart from the hydrates, are there any other opportunities in the future?
Well, all of the shales that we're pursuing right now in North America are source rocks, and they source the conventional deposits. The reason we're ahead perhaps is because we've just exhausted a lot of the easy, high-quality conventional reservoirs. And so if you look at other parts of the world, like, for example, Russia or the Middle East, you have fabulous source rocks. I mean, you have the Bazhanov Shale in Siberia. You've got very simple geologic conditions, not faulted like China and Europe, but very, very welcoming to horizontal drilling and fracking. So I think, you know, you have just enormous deposits that are not being pursued because they're not the low-hanging fruit. They are the uncooperatives. But eventually they'll be there, and I'm sure Russia will certainly pursue it, and perhaps the Middle East too.
Okay, Mike, my last question is for you. Shale gas in 30 years, what will happening?
I'm just going to pull out my crystal ball here and Madame Zelda performing. I think one of the critical aspects is that nominally 15, 20 years from now, I think shale gas will be what we will consider mainstream. It won't be considered unconventional at that time. But there still will be challenges, and the technology will continue to evolve. Companies will now be looking at areas of more challenging rocks that need to be produced, rocks that perhaps don't have the same fracture capabilities, perhaps they have higher water saturations. All of those aspects in that right now it's perhaps a bit presumptuous to say that we're taking the low-hanging fruit of shale gas, but we are in a sense that we're looking at rocks that will perform from a fracture stimulation perspective that's going to allow us to yield these hydrocarbons. As we advance the technologies in terms of drilling and stimulation, I think we'll be moving that envelope into other regions where the rocks are not as cooperative as the ones that we're currently exploring. I think another aspect is that it's important to recognize that assuming that shale gas production or natural gas production, both on a global scale, has its 10 to 20 year type of decline curves that we all are projecting, we still are looking at a huge amount of natural gas available to the society as a whole on a global scale. That allows us to use natural gas as a foundation for innovation and technology development in perhaps non-conventional non-hydrocarbon sources of energy. If we use that as a foundation, we now know that we have reliable, relatively low cost, reliable, and available energy that we can build upon. I just wanted to expand very briefly on what Scott was talking about in terms of hydrates, because that really is the next frontier in terms of unconventional resources. And it's absolutely staggering the amount of resource potential we have. In Canada alone, we have about 28,000 trillion cubic feet of gas estimated to be in the hydrates. Much of that lies within the Arctic region. And there was a well drilled back about 10 or 15 years ago called Malik number 1, which was a consortium of various governments and industry looking at producing gas from a hydrate deposit, relatively shallow, 500 meters depth. And it was technically feasible. There are lots of challenges. You're taking effectively a gravel that's held in a consolidated mass of natural gas and water, and when you disassociate it, turn it from a solid back to a gaseous form, now you have huge issues in terms of wellbore stability, in terms of pressure regimes, all of these aspects in terms of technologically, how do we drill an unconsolidated material and produce a hydrocarbon that the more you produce it, the more unstable the reservoir becomes. But I think it's really important just because it's a good segue towards some of the discussion we had this morning in talking about renewables, is if you look at the climate change discussions and some of the graphs that were shown this morning, and we talk about the shrinking ice sheets of northern, of Canada and the Arctic region, is there are some real risks involved in terms of the natural disassociation of the shallow calthrate or hydrate deposits lying underneath the permafrost of releasing methane into the atmosphere. And so while we say that 2030 we will have companies starting to explore for the technologies of hydrates, which will be a fuel of the future, I think that if the climate changes that are occurring continue along that path, that time frame in order to explore and start to look at the technologies of hydrates, particularly in the Arctic region, the shallow Arctic regions, may be forced upon us sooner than we were expecting.
Okay, so thank you very much.